Thank you. So, good afternoon, everyone. Thank you so much for giving me your time to go listen to this talk. So it's going to be about a tool called Javy, which is a way of taking JavaScript source code and converting it into a WebAssembly module. So I'm Jeff Charles. I'm a senior developer on the Wasm Foundation's team at Shopify, and I'm one of Javy's maintainers. So in this talk, I'm going to go over what is Javy, how to write some JavaScript for Javy, why we made Javy, and then we'll get to the interesting bits where we take a deep dive on different ways that we transform JavaScript source code into a WebAssembly module. And then I'll also cover how we use some of the underlying tech inside Javy to go and add additional functions into the JavaScript execution environment. So kicking off with what is Javy? Well, sort of the tagline mentions, it's a way of converting JavaScript to a WebAssembly module. More concretely, it's both a command line application and a WebAssembly library. So the command line application takes JavaScript source code as an input argument and outputs a WebAssembly module as output. Simple enough. The WebAssembly library has exported functions that can compile JavaScript source code to Quickjs bytecode and an exported function for evaluating Quickjs bytecode that's been provided to it. The internals of Javy are used by many of the companies here, and I'll be giving them a bit of a shout out when we get to a brief tour of that internal piece a little later. Another important piece about Javy is it targets Wazi as basically the API layer it uses to communicate. So this is unlike something that targets a browser environment or web APIs like Emscripten. So this is more typically used on the server side, but could be used in the browser with a Wazi shim. So in terms of like how we expect people to write code for Javy, is it uses top-level evaluation. So this is a bit different than what you would normally see with things that compile to WebAssembly, where there's an exported main function or a series of exported functions, and then execution enters at those points. Instead, the execution of the JavaScript starts at the top and goes line by line by line and invokes in that way. But what we do is we wrap that in the Wazi command pattern. So the Wazi command pattern is you have a function called _start, doesn't take any arguments, doesn't return any values. So you invoke that, and then we start evaluating the JavaScript code. And then we use Wazi's standard input, standard output, and standard error streams for I/O to the host. So that is, we take the input over standard input as a collection of bytes, write the output over standard output as a collection of bytes, and write to standard error, usually assuming it's going to be a UTF-8 encoded string. So go over a bit of a code example. So given an input that looks like foo1, that's encoded as JSON, increment the foo parameter. I do want to call out, though, that Javy doesn't require that you use JSON. You can use any format that can be provided as an array of bytes as input. In this case, I'm just using JSON or a JSON string because, hey, it's a lot easier to see what that is compared to, say, like that is protobuf. So starting at the top, we do our imports of basically stdio, which is an enum of the 3 streams, and a couple helper functions, read file sync, write file sync. This comes in from a package that's on NPM called Javy. And the reason we have it on NPM is we want to decouple the release cycle for these helper functions from the built-ins inside Javy that are perhaps a little less user-friendly to work with. And then this step's pretty straightforward. Read the bytes in from standard input, go run it through a text decoder to get back a JavaScript string from the UTF-8 character byte array, and then we parse that JavaScript string into an object, increment the parameter, the interesting part, and then reverse out the whole process, re-encode it back into JSON, take that JavaScript string, put it into a byte array of UTF-8 characters, and then write that out over standard output. And then here's where things get a little different from perhaps how people are used to working with JavaScript and how people are used to working with languages like Ruby with a virtual file system, is because this example involves multiple JavaScript files, we have to bundle them to actually put them through Javy. So we run a tool, we run ESBuild, but you can use Vite, you can use anything else that'll basically take a collection of modules and bundle them together and then get your output JavaScript file. And the reason you have to do that is Javy has no concept of what require means or what import means. So you do need to actually go and do that conversion. And then we call Javy compile, give it that bundled JavaScript file. We give it the WebAssembly, the name of the WebAssembly file we want it to output. And then you can just use Wasmtime and the name of the WebAssembly file, and that'll go and invoke that, that start function that's part of the Wazi command pattern, provide that JSON string as input here, and you get back your parameter incremented. Easy enough. So again, to give a bit of context, so why did we build Javy? So Shopify, for anyone in the room who doesn't know, it's an e-commerce platform. It's hosted software. And as part of that, we want to allow our partner developers to customize parts of the back-end logic. So examples of that are, as part of the checkout flow, we might want to offer custom discounts to, I don't know, people with the first name Jeff. Or we might want to go and hide different types of payment methods or delivery options. So this is how we let third-party developers alter our back-end logic, is by inserting a bit of WebAssembly code that matches an API. And where things get a little interesting is because this runs as part of our checkout flow, and in e-commerce, slow checkout means lost sales. These need to operate very, very, very quickly. They need to finish executing in under 5 milliseconds. And as part of having that fast loading of the WebAssembly, we also want to very aggressively cache these WebAssembly modules. So we impose a tight size restriction of 256 kilobytes on the size of the modules. This unfortunately does exclude a number of possible ways to compile WebAssembly that need to include more base code to execute. Now, you don't need JavaScript for any of this. Obviously, you can write it in TinyGo, Rust, Zig, C++, all sorts of languages will meet these requirements. But our partner developers expressed an extremely strong preference for wanting to write their code in JavaScript or TypeScript, because these are the languages they know. They don't want to have to learn a new language to use our platform. As well, we didn't want to run an additional non-WebAssembly runtime to go and execute these JavaScript functions. We wanted to use the existing WebAssembly runtime that we had. So we needed a tool that could go and take JavaScript and then convert it into a WebAssembly module that we could execute. So getting a bit more into the depth part of this talk, how we create WebAssembly that runs JavaScript. So the first piece I'm going to start with is called JavyCore. You can think about it like a Rust, it's essentially a Rust application. So first, starting from the left, we have Quickjs. This is a C library that includes a JavaScript interpreter that's ES2020 compatible. We take that and we wrap it with a crate. So crate we call Quickjs Walls Sys. It's a way of just adding Rust bindings around the Quickjs crate. And importantly, these bindings target a Wazi, like a Wazi target, as opposed to a native target. And then we wrap that sys crate with a crate called Quickjs Wasm I, and that adds a more ergonomic API around the raw Quickjs bindings. And I'll go into a bit more detail about what the API around this crate looks like in a few minutes, because it is really interesting. Then we add some I/O code. So this is essentially like text encoding, text decoding, hooking up the Wazi streams to functions that we inject into the JavaScript environment. And then we export a couple functions. So we have that start function that I mentioned earlier that just triggers module evaluation. But the interesting one's this Wizer initialize function, which I'm going to get into in a second. So going up a layer to the command line application, we actually embed that JavyCore WebAssembly module inside the CLI application itself. And when we ask Javy to compile a module, the first thing we go to is a tool called Wizer. Now, Wizer, for anyone in the room who's not familiar with it, is a bytecode alliance tool that allows you to run Given a WebAssembly module that has an initialization function, it'll instantiate the module, and it'll invoke a Wizer initialize function that's exported from that module. When that's done, it'll take the memory in the instance and then snapshot it into a new WebAssembly module, along with some code to basically dump that back into memory when that module starts. Now, normally it doesn't let you call imported functions, but you can configure it to run Wazi functions that are available. So what we do is we make the JavaScript source code available over the standard input stream to JavyCore. And in that initialization function, we read the JavaScript source code over standard input, and then tell Quickjs, hey, compile this to Quickjs bytecode. Let's store that in memory. Let's initialize the JavaScript context. Let's store that in memory. And then that all gets snapshot out to a new module that's configured with that start command to go and load that JavaScript context and then start evaluating that bytecode. So zooming out a bit, we see we have that Javy core piece that's embedded in that CLI piece, goes through Wizer. We're not quite done yet. We go through Binaryen's Wasm as a final step. And this basically runs a series of optimizations that goes to shrink the module and allow it to run faster. And then we get out the final module that we give back to the developer. And as promised, quick tour of Quickjs Walls. This is a crate that's used by a number of companies in this room, including Xdism, including Suborbital, including Fermion, and including VMware. So the two high-level concepts that we have in Quickjs Wasm are context and value. So context roughly corresponds to a Quickjs context. So this allows you to do things like create new JavaScript values, to basically insert Rust functions into your JavaScript environment, into doing things like executing jobs that are pending on the event loop, see if there are jobs pending, just all the sort of logistical stuff you need to do with the JavaScript environment. Oh yes, and evaluate code. And then the value piece corresponds with the JavaScript value. So that's your Booleans, your numbers, objects, things like that. Now, the really cool part about value is that it also includes third-day support. So if you have some JSON and you want to just convert it straight into a JavaScript value, we let you do that, and vice versa. If you have a JavaScript value and you want to get JSON or message pack or any other third-day supported format out of it, again, support's built in to go do that, which is super convenient. And then we use this, as I say, to add some JavaScript APIs. So in our case, we use it to add text decoder, but say you wanted to make a network connection and hypothetically you wanted to call it fetch. That's something else that you would be able to use a similar approach to what I'm about to outline to do. So we start off with, in this case, some JavaScript because it's a bit easier to actually express classes with JavaScript. And then we have some boilerplate code around it to help clean up the global object after we're done defining things. Now, the TextCore class itself isn't too interesting. There's a decode method on there. And then in there, we actually invoke a function that we're injecting into the environment off of the global object called Javy decode UTF-8 buffer to string. So again, we use that context to go and evaluate that code to pull it into the JavaScript environment. And then to add that method, or that function, sorry, that we're going to be using, we get the global object off of the context. And we go and we call wrap callback on that, basically on the context, and pass it a function that happens to return a closure that matches a particular signature. So that signature is, we take in the JavaScript context. So again, you can do things like create values, which is super useful. We have the this parameter that gets sent through. So if you're working off a class, you have access to that. And 0 or more arguments that get taken in as input. And then we return back a result of value. So in the OK case, you get the value back. In the error case, it throws an exception. And we have some particular, error type that you can use if you want to customize what kind of exception gets thrown. So this all works great. We get our JavaScript, we get our WebAssembly module out of this, and everybody's happy. Except, if you'll remember earlier, I mentioned we have a size limit of 256 kilobytes, and the smallest module that this approach produces is 870 kilobytes. So not super great for that use case in particular. but enter dynamic linking. So the idea here is we basically separate out the Wasm modules. So we have a Wasm module that contains the user's code, and we have a Wasm module that contains the JavaScript interpreter. So for context, like we call it the provider at Shopify because it provides a Quickjs execution environment. And the way these two get glued together is we use Wasmtime to actually execute these modules in production. And Wasmtime exposes this concept of a linker. And the neat thing you can do with the linker is you can say, OK, if I have imports that I'm pulling in under this namespace, and this other module has exports that correspond to the second part of the namespace for the import, you can hook those up with the linker and basically say, like, OK, if I want something called eval bytecode from Quickjs provider, well, the provider comes in under Quickjs provider, and it has an export called eval bytecode. Cool. When I go and import that, I'm actually importing the eval bytecode in the module that it's being exported from. And then at a high level, and I'll go into some details exactly how this works, is we have the JS Code module that imports memory and functions from the provider module using that linker in Wasmtime. And we use a memory allocation function defined in the component model to basically have the one module or the one instance manage memory in the other instance. So we're using these little pieces that exist today inside Wasmtime and exist today as part of the component model specification to go and coordinate all this to basically give us more options than we had before. So again, that provider library looks very similar to the Javy core piece. We have that Quickjs Wasm RS piece with, again, Quickjs embedded inside of it. We have very similar I/O code. But our exported functions are different in this case, because again, this is that WebAssembly library piece I was mentioning earlier. So we have the first method, it's canonical ABI realloc method. So this is part of the component model. It's used for basically having one instance manage memory inside of another instance. So this is how we're able to basically move things between modules and have it be somewhat coordinated in a standard way. And then we have that compile source method that basically expects you to use the realloc method to go and put some JavaScript source code inside the provider's linear memory, and you go and give it the address to that source code, and like that source code, and compile source gives you back a wide pointer to the Quickjs bytecode it's produced. And we have an eval bytecode exported function that again expects a wide pointer to the Quickjs bytecode that's been inserted into the module or into the instance. So at CLI level, the way we do the embedded linking, we embed this provider Wasm library, again, as a library embedded in the command line application, and we use Wasmtime to instantiate it and work with that library. So at the command line level, we call compile source. So we go and we take that user source code, run it through compile source, get the bytecode back, and then we use a crate called Wasm encoder to go and actually write out the code module. So the code module that we output looks, well, like this. Again, series of imports, and then a start function, and then a data segment containing the bytecode. So first we pull in that canonical ABI realloc function. We pull in the eval bytecode function. Those both come from the provider module. And then we import memory from the provider module to give this instance access to the memory. This instance itself doesn't need its own memory, thankfully, with the way the start function is currently implemented. But if it did, again, it's possible for this instance to also define its own memory, and then you would need the multi-memory proposal enabled in the environment that you're executing this module in. But since we don't need it, we're able to keep it at one memory, so we don't need that, so it runs in more environments. And then zooming into that start function, we start by, again, calling realloc to go and get an address to where we can go and put some Quickjs bytecode. So that function signature, for anyone in the room who's not familiar with the realloc function in the component model, we have zeros for the original pointer and the original length because we didn't have previous allocation. We give it an alignment of 1, and then we say, give us bytecode length amount of memory. And at this point, it's a constant value. We know what the bytecode is, so when we're creating this module, we can just stamp this in as constants wherever we need to. And then, given that we have that memory address to go and write the bytecode to, we call the memory init instruction, which basically says, hey, take this data segment and go and put your entire contents inside this memory address, please. And so we give it the bytecode data segment that contains the bytecode, and we give it the address of the memory we just allocated, tell it to start at the beginning of the data segment, and tell it the amount of memory we want transferred out of that data segment into the basically that memory address we just allocated. And then we drop the data segment because we don't need it anymore. And then the big step, calling evaluate bytecode. Again, giving it the address where we just copied the bytecode to and the bytecode length, and off it goes. And then actually what this looks like in terms of like creating one of these modules and executing it. So we have the echo command to basically write out a simple hello world program in JavaScript, write that into a JavaScript file. We do that similar Javy compile call. But this time we pass the -d flag to go and indicate that we want it dynamically compiled. If you don't pass the -d flag, it's just going to compile it statically. So that's default. And then we do this interesting thing with this Javy emit provider call. So normally, this isn't something that someone would need to run, except if they wanted to execute this code locally or otherwise wanted to get our WebAssembly library. Because there aren't really a lot of widely available options at the moment for distributing WebAssembly libraries, and because the library is embedded in our CLI, we decided to add a subcommand to go and actually get the library from the CLI itself. So for something like this, it's super convenient. And then for running this, again, it's a very similar Wasmtime run command where we just tell it to run the example. But we do need to pass an additional flag to basically tell Wasmtime, hey, if you see an import for Javy Quickjs provider v1, go and use that file that we just basically output from the Javy CLI so it's able to actually link it in. And then we run it, and we get back our hello world as expected. So again, just to reiterate sort of what we went over what Javy is, how to write some high-level JavaScript code for it, what that looks like, what the input and output flow looks like. We went over how to create modules with Quickjs embedded inside the module. We went over a quick tour of Quickjs Wasm I, which you can use today to build all sorts of applications that use WebAssembly and compile those into WebAssembly modules so they can be executed in a variety of environments. How to use that to go and add your own custom JS functionality into a JavaScript environment that you're hoping to offer, as well as how we go and we create these tiny modules that are about like 3 kilobytes in size for an interpreted language that normally requires modules that are at least 870 kilobytes in size. Thank you so much. Please go visit our engineering blog. And it looks like we have about 6 minutes for questions. So does anyone have any questions?
Hey, Jeff. Great talk. I was wondering if you have plans for leveraging the GC proposal.
Not at the moment. Okay. We are keeping an eye on it. For context, with Shopify functions, because they have to execute in, because they have to execute in less than 5 milliseconds, GC typically doesn't run in our case. So it's not really a concern from our side, but obviously for Javy, the tool itself would be useful for other use cases potentially.
Very cool. I also wanted to say that we've been playing around with Javy at Loophole, and it's super great. So,
awesome.
Thank you.
Yep.
First of all, great talk. You mentioned the use case for WebAssembly at Shopify was this if and buts in the checkout flow. Could you share some more on what Shopify wants to use WebAssembly for in your business?
Oh, yes. So it's basically Shopify is like hosted code, right? So it's not like an open source project like Magento, and it's not a self-hosted product. It's hosted on our servers. And we have third-party developers who want to customize parts of the checkout flow and like do things like add discounts, hide payment methods, things along those lines. And we wanted a way to do this securely and quickly. So WebAssembly allows people who aren't Shopify developers to go and change code on our back end, essentially, and alter the business logic of the checkout flow.
So that could potentially expand to other use cases than
Yes.
just the checkout flow?
Oh, absolutely.
Yeah.
Yeah, thanks for the talk. So my question is about security. So with one module, with a big module, with Quickjs, you have a security. But with dynamic linking, you have a, as I understand, a shared heap inside Quickjs for each client. I mean...
No. So actually, we instantiate that Quickjs provider module separately for each instance of the Quickjs bytecode. So the module is the same. We have the same module across all of the users of Quickjs, but a different instance of that module per execution or per Quickjs bytecode containing module.
Oh, yeah, I see. Thanks.
Yeah.
Hey, great talk. Do you have any data on the overhead between the static linking monolith and the dynamic linking, like especially with the extra compilation step involved, and the snapshot of the monolith that gets that extra boost from Wizer?
Yeah. We do have benchmark numbers. They are internal. I don't remember the exact numbers off the top of my head, unfortunately. But yeah, we did do the numbers. The dynamic linking actually usually is faster because it is a smaller module. They are in like the single kilobytes, and we can use the initialize pre method on the shared engine module to basically speed up initialization time because it doesn't need to check that the imports are all satisfied every time it runs.
Sweet, thanks.